All right, let's talk about instantaneous reaction rates and mechanisms. Mechanism is kind of the big one I want to hit in this, but instantaneous rates are good to know too because, well, what we're looking at really is an instantaneous rate. I showed you earlier, right, this picture, right? So this shows you the concentration of our NO2 as it's making NO and O2, right? As this is breaking down, it's a decomposition reaction, right? Starts off up here, and then the concentration drops, right? So as this is disappearing, it's becoming this and this, right? So this is being consumed, so our concentration is getting less and less and less and less. The rate of the reaction is basically the change in the concentration over the change in time, right? That's the slope. All right, so that's a slope at any point along this curve. So we always start off, our reactions are always fastest at the start. All right, then as we use up the reactant, that rate slows down, slows down, slows down. All right, but once we figured out our rate law, all right, so once we have the rate law here, so I have rate equals K NO2 squared. If I want the rate at any point here, I can just plug in that concentration and calculate the rate. So once you know the rate constant stuff, it's kind of cool. So you don't actually need the graph or need to actually get a slope, but it is a slope. All right, let's get to mechanisms. All right, reaction mechanisms. All right, so what's a reaction mechanism? All right, so a chemical equation is going to describe a reaction, but it doesn't give you all the nitty gritty. All right, the nitty gritty is from the reaction mechanism. So let's say I have H2 plus I2 makes 2HI. That's a chemical equation. That shows me what happens. But do you think it really is just an H2 and an I2 just boop, come together and they make 2HI? Maybe you've never even thought about it, but think about it. Like, do you think it happens just like it's written? Many, many reactions do not happen exactly as they're written. Like, overall, this is what happens, but how this occurs, it goes through a series of steps, all right? And that series of steps is what we call the reaction mechanism. It's the step-by-step sequence of reactions by which the overall chemical change occurs. And more on the next slide. Okay. So yeah, we're going to talk about some HI proposed mechanisms there, but before we get there, let me give you some vocabulary, some stuff to need to know. All right, things that are formed in an early step of a mechanism then get consumed in a later step of a mechanism, those are intermediates. They're reaction intermediates. So they get produced early on and then consumed later on. They don't show up in the overall equation. All right, so those are known as reaction intermediates. A simple reaction, also known as an elementary reaction, that's something that occurs in a single step. So it doesn't go by a mechanism. So the steps in a reaction mechanism, those are always simple reactions. They occur exactly as they're written. A complex reaction occurs in 2 or more elementary steps. So a complex reaction is made up of a bunch of simple reactions. And your reaction mechanism, that's the complete sequence of elementary steps that make up a complex reaction. And so now we're all on board. So now let's look at some possible reaction mechanisms for the formation of hydrogen iodide. All right, so let's say we can have iodine splitting up into 2 iodine atoms. Then those 2 iodine atoms, they react with hydrogen molecules. They make the 2HI. Cool, that's fine. Or mechanism number 2, all right, a 3-step deal. Iodine makes 2 iodine atoms, kind of like the first one. But this time, one of the iodine atoms sticks onto hydrogen, makes this H2I. And then that H2I hits an iodine atom, makes a 2HI. Boom. So when I add this up, this plus this, it equals this. When I add this, this, and this, it equals that, right? The iodine atoms, those are an intermediate, produced in an early step, consumed in a later step. All right, boom, 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 produced in an early step, consumed in a later step. This one also has a second intermediate, the H2I. Boom. So which one of these mechanisms is correct? Don't know. All right, we can never prove a mechanism. We can disprove mechanisms, but we can never actually prove a mechanism. We can't get in there at the molecular level and watch this happen, but we can disprove it. So let's say this H2I stuff, let's say it had some kind of telltale color to it or something, and we have some really fancy detectors that could spot H2I, that are really good at spotting H2I, incredibly good. And so we do this reaction while watching it with our specialized equipment, and we never, ever, ever see any evidence of H2I. All right. It's possible that it's just being formed and consumed so fast we're not seeing it, but it's also not looking too good for this mechanism. Like, nobody in the world is spotting any H2I. All right, so it might kind of not bode well for this guy. All right. let's get into some more stuff here. So the form of your rate law depends on the reaction mechanism. If you have a reaction that occurs in a single step, all right, like an elementary step, like one of the steps in a mechanism, it's an elementary reaction, right? What we can do is our coefficients become the exponents. All right, that's what's really nice. So I can just look at this. If I know this is a simple elementary step, happens exactly as it's written, there's a cheat. All right, the coefficients become the exponents in the rate law. So you can write the rate law without going to the lab and doing all those experiments where you measure how A changes the rate and then how B changes the rate and coming up with this. If you know this is a single step process, you can just go, oh, coefficient becomes exponent. That's a 1, that's a 1. Boom. All right. So we can do this if we're looking at a mechanism. So if I'm looking at a mechanism, looking at all the different steps of a mechanism, I could really quickly come up with a rate law for each of those steps. All right. How are you going to know that something occurs in one step? I'm going to tell you. All right. I will say this happens in one single step. And so you'll know, and you go, oh, I can use that trick. All right. People in real life are not as lucky. They don't go into a lab just automatically knowing, oh, this is a single step thing. They have to do all sorts of shenanigans to figure out what's going on. All right. Ooh, what about the reverse reaction? So if I reverse this reaction, right, do you think K is the same? Do I have a different rate law? I would totally have a different rate law. Let me see. Let me get my pen. Let me see if I can get a pen out here. Pointer options, pen. All right. So let me flip back to this guy. All right, so A to B. So the reverse, I'm just gonna write it on this slide here. So the rate law for the reverse reaction, I'm gonna write rate, if you can stand my terrible writing here, equals, all right, rate constant. And this is gonna be depending on the concentration of A to B, all right? Because going backwards, this is my reactant in the reverse reaction, right? So the other question I think was going to pop up on this next slide was like, do you think these Ks are the same? And the answer to that is they are definitely not the same. So if this, let's say that this is an exothermic reaction in the forward direction, right? Whoosh, you got that thing going on. If I go reverse, right, it's endothermic in the reverse direction, the activation energy is much larger going in the backwards direction. So inside of K, it's kind of like the orientation factor, the activation energy, those are all kind of hidden inside of K. If you take AP chemistry, we'll actually get inside of K. You'll get to see like where exactly those are. Like, what do you mean? It'll make more sense if you take AP. If not, don't worry about it at all. But those things are kind of swallowed up inside of K. So yeah, it's definitely a different constant going backwards. All right, so what about that? It's written as a rate constant same? Definitely not. If a chemical reaction proceeds in a sequence of steps, the rate law is determined from the slowest step because it has the lowest rate. All right, that slowest step is called the rate determining step. So the rate law of the overall reaction always matches the slow step of your mechanism. All right, so the slowest rate step is called your rate determining step. All right, it's where it bottlenecks. So let's say, for example, right, we got this bunch of funnels here. So we have an overall reaction. R becomes P. So reactants become products. All right. But let's say it's actually a 3-step deal. R becomes A becomes B becomes P. R goes to A really quick. No problem. Here's the bottleneck. Here's the rate determining step. It's really small here. It's like this totally slows down and jams up. Right. A finally becomes B. But as soon as you have B, poof, becomes P instantly. There's no hang up here. This is where it all chokes up. It's the rate determining step. This cannot get through here any faster than right here. This is what determines the speed of the whole thing. And it doesn't even matter where we put this in the sequence. It could be first, last, anywhere in between. It will always determine the overall rate of your reaction. So that's what that rate determining step is. It's like the bottleneck. All right, that's where it goes, kind of chokes things up. All right, that's probably a little slide, a couple more slides here, and we'll call it done for this chapter, actually. So let's say I have this reaction. NO2 plus CO goes to NO and CO2. We believe it's a 2-step process. So we think this is a 2-step process, and it has the following mechanism. So step 1 is 2NO2 goes to NO3 and NO. Step 2, NO3 plus CO goes to NO2 and CO2. All right. Here's the deal. Right, this is an elementary reaction, so I can write a rate law, right? I can say rate, I'm just going to call R. So I'll call this K. And for this one, right, so the coefficient becomes the exponent. So NO2 blip squared. The rate for this one, I'll call it, that's a K. That's the worst looking K ever. I'll call it K2 because it's step 2. This would depend on the NO3 concentration and the CO. All right, so this is a little funky too because NO3, if you're paying attention here, you're like, wait a minute, that's an intermediate. All right, in AP, I show you guys how to deal with that. But our experimental rate law should match the slowest step. And so experimentally, we know that the rate law is this right here, right? What do you know? That matches this one. So what does that mean? That means step 1 is slow. That means this is the slowest step in the mechanism. So your experimental rate law will always match your slowest step in the mechanism. That's kind of what I'm trying to get across there. All right, last slide. Clicking some buttons here. All right, your elementary steps, they have to add up to give the correct overall balance equation. So if you're looking at a mechanism, like one of the first things to check is like, well, do these all add up? Your rate law for the rate determining step will always match the experimentally determined rate law. So if you have an experimentally determined rate law and it doesn't match any of the steps of the proposed mechanism, that would also mean your mechanism is junk. It is no bueno. All right, and then last little thing here, just remember, mechanisms can never be proven. We can disprove them, but we can never actually prove them. I think that's actually it for this chapter as far as lectures go. All right, catch you guys in the next one. The end is near.